In this video, we are going to talk about how to sketch hyperbolic functions. So for example, let's assume we have the function y is equal to hyperbolic cosine of x. How do we sketch this function? The way to go about it is to define the hyperbolic cosine of x. So we know that y is equal to cos x can also be written as half of exponent x and plus exponent minus x. So now, what we need to do is to find the y-intercept. But we know that for the y-intercept, x is equal to 0. So let's find y of 0, and this is equal to half of. Now, this becomes exponent 0 plus exponent 0. Exponent 0 is 1. So 1 plus 1 is 2, and 2 divided by 2 is 1. So y of 0 is equal to 1. So it means that we have a y-intercept at the point 0, 1. Now, let's look at limits at infinity. Now, as x approaches infinity, that is positive infinity, what happens to y? Now, let's talk about these two functions, exponent x and exponent minus x. I want to write exponent minus x as equal to 1 over exponent x. So in reality, we are dealing with exponent x and then 1 over exponent x. So as x approaches infinity, you will see that exponent x will go to infinity, and then 1 over infinity is 0 for 1 over exponent x, and therefore this function goes to 0 whilst this one goes to infinity. So it becomes infinity plus 0. That is a very big number plus 0, and that will give us infinity. So as x approaches infinity, you see that y approaches infinity. Now, as x approaches minus infinity, what happens to y? Now, you see that this exponent x becomes exponent minus infinity, and that approaches 0. And then 1 over exponent x will become exponent infinity, and that approaches infinity. So it becomes 0 plus infinity, and that will give us infinity. So as x approaches negative infinity, y approaches infinity. So we said there is a y-intercept, which is 0, 1. So here is supposed to be 1. And then we've said that as x approaches positive infinity, y approaches positive infinity. That is this way. So, but we know that this is the y-intercept. So that side of the graph is going to look like this. And then as x approaches negative infinity, y approaches positive infinity. So this side of the graph will also go like this. So you see that the graph of y equals cos x will look like this. So this is the graph of y equals cos x. Continuing from where we left off, this is the graph of cos x that we sketch. So let's determine the domain. What is the domain of this graph? The domain of this graph is, you can see that for the x values, it ranges from negative infinity to infinity. So the domain is negative infinity and then infinity. So that's the domain of this graph. And then for the range, let's also find the range. The domain talks about the set of possible x values, and then the range talks about the set of possible y values. And you can see that the minimum y value is 1, and the 1 is inclusive. So therefore, it becomes 1 and then positive infinity. So this is the range. Now, having sketched the graph of cos x, what if y is equal to cos inverse of x? How will this graph look like? Now, there is a rule of thumb that says that to be able to sketch the graph of cos inverse of x, the inverse hyperbolic functions, we need to reflect the graph in the line x, y equals x. So this is the line y equals x. So if we put a mirror here and we sketch this graph, then the graph that we sketch from here will be this graph, which is cos inverse of x. So if we put a plane mirror here, the one comes here. And then now, aside that, you see that this graph, if we draw a horizontal line through it, the horizontal line will touch the graph at 2 points. So this curve fails the horizontal line test. And if a graph fails the horizontal line test, it means that its inverse cannot be a function. So if we were supposed to sketch this graph, then it would have looked like this. But then if you use the vertical line test, this graph will fail. So because of that, we are only going to reflect this part of the graph in the line y equals x, because that's the only part that will pass for the vertical line test. So we can only draw the hyperbolic inverse for one side of the graph, and therefore it's going to look like this. So this is the curve y equals cos inverse of x. So now let's write the domain of this curve. So with the domain, you see that now the least value starts at 1. So, and 1 is inclusive. It is 1 and then infinity. And then the range, for the range, you see that the least y value is 0. So it becomes 0 and then infinity. Sorry, 0 is inclusive. So this is 0 and then infinity. So now, what if y is equal to hyperbolic sine of x? How will this graph look like? So let's define the hyperbolic sine of x. So in that case, y is equal to half of exponent x, then minus exponent minus x. Now, let's look for the y-intercept. So what is the y-intercept for this curve? So for the y-intercept, we need to find y of 0, and that is equal to half, and then exponent 0 minus exponent 0. So you see that it is y is equal to y of 0 is equal to 0, and therefore we have a y-intercept at 0, 0. Now let's look for limits at infinity. So as x approaches infinity, remember that we are talking about exponent x and then 1 over exponent x. What happens to this curve? Exponent x approaches infinity, but 1 over exponent x approaches 0. 0 plus infinity is infinity. Sorry, infinity minus 0 is infinity. So as x approaches infinity, y approaches infinity. Now, what about x approaching negative infinity? What happens to y? You see that the exponent x, this part, will approach 0, but 1 over exponent x will approach infinity, but there is a negative sign here, and therefore y will approach negative infinity. So having gotten that, then let's go ahead and then sketch the curve. So here's x, and then this place is y. So at the end of the day, we know that there is a y-intercept at 0, 0. And then we are saying that as x approaches positive infinity, y approaches positive infinity. So what it means is that this part of the curve is going to look like this. And then we are saying that as x approaches negative infinity, which is this place, y approaches negative infinity. So it goes here. So this side of the curve will also look like this. So this is the curve. Let me sketch this way. So this is the curve y equals hyperbolic sine of x. Now let's determine the domain. The domain is from negative infinity to infinity. And then the range, you see that the range too is also from negative infinity to infinity. Now, what if y was hyperbolic sine inverse of x? How will the graph look like? So to find the inverse function, we need to reflect this graph in the line y equals x, that is this place. But because this graph passes the horizontal line test, because any horizontal line we draw will cut the graph at one point, it means that the inverse will exist for all values of x. So sketching this, so this is y and then this is x. So if we reflect this, you see that this part will go this way and then this part will go this way. So this is how the graph is going to look like. So this is the graph of y equals hyperbolic sine inverse. So y equals hyperbolic sine inverse of x. So now let's determine the domain. The domain is d is equal to, now you see that all the x values pass from there, so will work. So it's minus infinity and then infinity, and then the range, all the y values are also defined for this, so it's also minus infinity and then infinity. So what if y is equal to hyperbolic tan x? How will the graph of y equals hyperbolic tan x look like? So let's define the hyperbolic tan. Know that y is equal to exponent x minus exponent minus x divided by exponent x plus exponent minus x. So this is the definition of the tan function. So let's multiply the numerator and the denominator by exponent x. So this becomes y equals, if we multiply exponent x by exponent x, it becomes exponent 2x minus exponent minus x times exponent x is exponent 0, which is 1, divided by exponent x times exponent x is exponent 2x. Then exponent minus x times exponent x becomes plus 1. So now, because the highest power of the numerator is equal to the highest power of the denominator, it means that we can talk about the horizontal asymptotes. So we have horizontal asymptotes. We just need to divide the coefficient of the highest power of the numerator by the coefficient of the highest power of the denominator. And therefore, we have horizontal asymptotes at y equals 1. Now, instead of multiplying by exponent x, let's multiply by exponent minus x. So y is equal to exponent x times exponent minus x is 1. Then minus exponent minus x times exponent minus x is exponent minus 2x. Divided by exponent x times exponent minus x is 1. Then plus exponent minus x times exponent minus x is exponent minus 2x. So because the highest power of the numerator is also equal to the highest power of the denominator, to find the horizontal asymptote, we just take the coefficient of the numerator and divide it by the coefficient of the denominator. So you can see that we will have horizontal asymptote at y equals minus 1. So we have horizontal asymptote at y equals 1 and horizontal asymptote at y equals minus 1. So for limits at infinity, what happens when x approaches minus infinity? So as x approaches minus infinity, exponent 2x will approach 0. And therefore this becomes 0 minus 1. So for the numerator, it is 0 minus 1, which is minus 1. And then for the denominator, here 0 plus 1, so divided by 1, and therefore y will approach minus 1. Then for here, as x approaches infinity, exponent minus 2x will approach 0, and therefore this becomes 1 minus 0, which is 1, divided by 1 plus 0, which is 1. 1 divided by 1 is 1, and therefore y will approach infinity. So this is minus 1, and then this is 1. So we know that there is horizontal asymptote here, and then there's also a horizontal asymptote here. Then we are saying that as x approaches minus infinity, that is this side, y approaches minus 1. So y will be approaching this way. And therefore, this side of the curve is going to look like this. Then as x approaches infinity, y approaches, sorry, here was 1. It's not infinity. Y approaches 1 because we say 1 divided by 1 is 1. So with this side, y approaches 1 is this way. So this is the graph of y equals hyperbolic tan of x. So let's determine the domain. The domain is all minus infinity and infinity. And then the range, see that the highest y value is 1, and then the lowest y value is minus 1. So it becomes minus 1 and then 1. That is the range. Now what about y equals hyperbolic tan inverse of x? So just as we said, you put a mirror here and then you reflect this graph to get that. So let's sketch that graph over here. So what it means is that the horizontal asymptote will become vertical asymptote at minus 1 and then 1. So there is a vertical asymptote here. And then aside that, if we reflect this part of the graph here, we are going to get it this way. And then if we reflect the down part too, this is how the graph of tan inverse of x is going to look like. So let's determine the domain. The domain is minus 1 and then 1. And then the range is minus infinity and then infinity. What if y is equal to sec x? How do we sketch the curve y equals sec x? So let's define it. So y equals sec x becomes 2 divided by exponent x plus exponent minus x. This is the definition of sec x. So now let's find the y-intercept. What is y of 0? It's equal to 2 divided by exponent 0 plus exponent 0, which is equal to 1. And therefore, there's a y-intercept at 0, 1. Now let's find limits at infinity. As x approaches infinity, you see that exponent x approaches infinity, and then exponent minus x approaches 0. So it becomes 2 divided by infinity, and that would be 0. So y approaches 0. And then as x approaches minus infinity, you see that exponent x will approach 0, but exponent minus x will approach infinity. 2 divided by infinity is 0. It will approach 0. So y will also approach 0. So let's try and then sketch the curve. Please, just before I forget, 2 divided by infinity will approach 0. It is not 0. So we know that there is a y-intercept at 0, 1. So let's assume here is 1. Now, as x approaches infinity, y approaches 0. So as x approaches infinity, y approaches 0. And then as x, so this one is going to look like this. And then as x approaches minus infinity, y approaches 0. So this side too is going to look like this. So this is the graph y is equal to sec x. So let's determine the domain. The domain is minus infinity and then infinity. The range, you see that the graph approaches 0, and therefore the lowest y value will be 0, and then the highest y value is 1. So 0, 1. So that is the range. Now what about if y was sec inverse of x? So let's draw that curve here. So here's y and then here's x. So if we reflect it in the line y equals x, you see that this one will move to this side. So the one will be here. But then the limitation is that this graph does not pass the horizontal line test, and therefore we cannot draw all of the graph as the sec inverse. So we only need to take one part. So if we take this part and then we reflect it, you see that this side will go here, and then this part will come down. So it's going to look like this. So this is the graph y equals sec inverse of x. So what is the domain of this curve? The domain is you see that the highest x value is 1 and then the lowest x value is 0. So it is 0 and then 1. And then the range is the lowest y value is 1. So it is 1 and then infinity. So this is the domain and then the range. What if y is equal to cosec inverse of cosec x? How will the graph of y equals cosec x look like? So y cosec x is defined as 2 divided by exponent x minus exponent minus x. So now with this, you can see that we have, if we put x equals 0, if we put x equals 0 into this function, you see that y will be undefined, and therefore we have vertical asymptote at x equals 0. Now, what about limits at infinity? As x approaches infinity, exponent minus x approaches 0, exponent x approaches infinity. 2 divided by infinity will approach 0. So y approaches 0. And then as x approaches minus infinity, exponent x approaches 0, but exponent minus x approaches infinity. So you will see that 2 divided by minus infinity, that will be, y will also approach 0. So y approaches, this is approach. So y approaches 0. And therefore, you can see that since y approaches 0, y is not 0. So the x-axis and then the y-axis are asymptotes. So we have this. Okay, so let me sketch the curve here. So the x-axis, the y-axis is the vertical asymptote, and then the x-axis is the horizontal asymptote. So it's going to look like this. This is y, and then this is x. The x-axis is horizontal asymptote, and then the y-axis is vertical asymptote. So we've said that as x approaches infinity, y approaches 0. So as x approaches infinity, then y approaches 0. So y will approach 0 as x approaches infinity. And then so it's going to look like this. And then as x approaches minus infinity, y approaches 0. So as x approaches minus infinity, y approaches 0. And this one too is going to look like this. So now, what is the domain of this curve? The domain is from here. You see that it's minus infinity and then 0, union 0 and then infinity. Then the range is also minus infinity and then 0, because the curve does not touch 0, union 0 and then infinity. Now we use this bracket when the point is not part, and then we use this bracket when the point is part. So what about y equals cosec inverse of x? How will that curve look like? So all we need to do is to reflect this line in y equals x. So if we do that, it means that the x axis becomes the y axis, and then the y-axis becomes the x-axis. So it's going to look like this. So this is x, and then this is y. And then if we reflect this, it won't change. It will still look the same. And then if we reflect this one too, it will still look the same. So at the end of the day, the domain and the range is going to be the same for the cosec inverse. So the domain is minus infinity and then 0. Union 0 and then infinity, and then the range is minus infinity and 0, union 0 and then infinity. Finally, let's talk about the graph y equals hyperbolic cotangent of x. So let's define hyperbolic cotangent of x. So y is equal to exponent x plus exponent minus x divided by exponent x minus exponent minus x. So now let's multiply through by exponent x. So y is equal to exponent x times exponent x is exponent 2x, then plus exponent minus x times exponent x is 1, divided by, here will be exponent 2x minus 1. Now, if x is equal to 0, what happens to y? You see that y becomes undefined. So it means that there is horizontal asymptote at x equals 0. And x equals 0 is y-axis. So it means that the y-axis is a horizontal asymptote. And then now, we can talk about horizontal asymptotes. Sorry. There is vertical asymptote. So this is a vertical asymptote. And then, let's talk about the horizontal asymptotes. So the highest power here is equal to the highest power here. And therefore, there is a horizontal asymptote at y equals 1. And then now, let's multiply by exponent minus x. So y is equal to exponent x times exponent minus x is 1. Then plus exponent minus x times exponent x minus x is exponent minus 2x, divided by 1 minus exponent minus 2x. So you see that in this case too, there is horizontal asymptote at y equals minus 1. Now, having gotten this, then let's look for limits at infinity. So you see that as x approaches minus infinity here, exponent 2x will approach 0. So this becomes 1 divided by minus 1. So y will approach minus 1. And then for here, as x approaches infinity, exponent minus 2x will approach 0, and therefore y will approach 1. So let's put all of this into the curve and then sketch. So this is the y-axis, and then this is the x-axis. Remember that we've said that there is horizontal asymptote as y equals 1 and y equals minus 1. So this is, let's assume here, no, let me bring it down. Let's assume here is minus 1, and then here is 1. So there is horizontal asymptote here, and then there is also horizontal asymptote over here. So as x approaches minus infinity, y approaches minus 1. So this curve is going to look like this. And then as x approaches infinity, y approaches 1. So x approaches infinity as y approaches 1. So this one too is going to look like this. So this is the nature of the curve. Now let's determine the domain. You see that with this, the y-axis is vertical asymptote. So the domain for here is equal to minus infinity and then 0 union. Then this side is also 0 and then infinity. And then the range, see that here is minus infinity, but 1 and then 1, because sorry, and minus 1, but minus 1 is not part. So and minus 1. So I made a mistake. Let me put the minus 1 union. Yes, 1 and then infinity. So this is the range. What if y is equal to the quart inverse of x? We only need to reflect this line or put a mirror here and then reflect the curve. So let me sketch it very little here. So this now has horizontal asymptotes here. So there is horizontal asymptote here. And then this horizontal asymptote will become vertical asymptote at minus 1 and 1. So this becomes a vertical asymptote, and then this one also becomes a vertical asymptote. Now this is y, and then this is x. So if we reflect this, it won't change. So this one will be here. And then if you reflect this one, it won't change. This one too will also look like this. So at the end of the day, the domain in this case will be minus infinity, and then minus 1 union 1 and infinity. And then the range in this case, you see that for the range it is minus infinity, and then remember we said that the x-axis is now a horizontal asymptote, so it is not part. So it becomes minus infinity and then 0 union 0 and then infinity.